Hi, and welcome to the last session of this first day of the unique Student Symposium 2022. During our in-person poster session here in Montreal, we are presenting a round of lightning talks online. We received these short 3-minute talks from students doing research at the intersection of neuroscience and artificial intelligence. If you want to spend more time on a certain talk or want to get in touch with the authors, the work will be online, available on our website soon. Now I wish you a lot of fun with this round of lightning talks.
Hi, my name is Etienne Saint-Onge and I'm presenting Tractor Search, an algorithm to find similar white matter pathways reconstructed by diffusion MRI. From diffusion MRI, we're able to estimate trajectory within the white matter. Then we often want to group those trajectories to similar ones. So for example, if we know a connection within the brain, we might want to find all the ones that are similar within our subject, and then apply it for all the known white matter pathways. To do this, we first simplified streamline using fewer points, and then we created a KD tree adapted for them. We also use a specific streamline distance that is simply the average distance along the trajectory. This have the nice property that if we take the barycenter of each streamline, we are guaranteed to have a smaller distance than the original full-length distance. And we can use that property to efficiently search for all streamline in a small radius. This search can afterward be used to reconstruct a sparse distance matrix, grouping or computing the distance between all streamline within a given radius. And this could be used to afterward cluster them together. We can use this approach to extract from a full brain tractogram all the streamline that are similar to a known white matter pathways. So for example, this corpus callosum template. So if we do the search, we can recover all those streamlines with different distance from the original template. Compared to previous approach, the proposed path streamline search is an exact approach where we can see that, for example, Rico bundle is missing some streamline in purple and red. In addition, the fast streamline search now with the LPQ tree is also a lot faster. If you would like to have more information on this method, don't hesitate to ask me. It was accepted in neuroinformatics, and you can find the detail and open source implementation on my GitHub page in Tractor Search or LPQ tree repository.
Hi, so good afternoon, everyone. Today I'm going to talk to you about the exploration of cognitive profiles in healthy children using unsupervised machine learning. So we know that neuropsychological tests are the most used to assess executive functions in children. Particularly, design fluency test offers a great way to assess multiple executive functions. Combined with machine learning, design fluency tests have been found useful in distinguishing cognitive profiles in children. So for example, in a study of Gauthier and colleagues in 2016, they used the 5-point test, which is a design fluency test, to compare ADHD children and controls, and they found 2 different patterns for doing the tasks. Unfortunately, few studies have explored the cognitive profiles in healthy children, and that will give us better insights in the heterogeneous nature of cognition in children. So the main objective of this study was to explore if different executive profiles exist on the 5-point test in healthy children using unsupervised machine learning. And a second objective was to compare different kind of unsupervised algorithm So for methods, we selected 113 children aged 7 to 13 years old. They were recruited in schools in Quebec. And they all underwent the 5-point test on tablets. So the 5-point test consists of drawing the most possible designs in 5 minutes by linking different dots. So here is an example of designs that can be made. For studies, we used the data for the number of designs made in every minute, also the number of repetitions made. So if the children do 2 times the same designs, we counted that repetition, and also the number of strategies for each minute. So all of them for 5 minutes. And so they were used as inputs for the self-organizing maps, which are essentially a way to project high dimensionality data into a 2-dimensional grid. So for our study, we used an 8x8 grid of neurons. And we also used a k-mean, which maximizes separations between groups and minimizes the separation within groups. So for results, both the sum and the k-means identified 2 distinct clusters. And we think those clusters were based on different speed accuracy trade-off, because when we look at the 2 clusters that were obtained, we found that the first cluster, so at the top, had a way higher number of designs produced, but also a higher number of repetitions, compared to the second groups, which had a lower number of designs, but also a lower number of repetitions. So we think that the first group had a tendency to produce the maximum number of designs, regardless of if they were making a repetition, while the second group was more careful. And so in conclusion, the sum and k-means yielded similar results because they found 2 distinct clusters, and even within those clusters, the participants were roughly the same in each groups. That also suggests that different profiles, cognitive profiles in healthy children exist. And that also underlined the importance of parsimony in our use of machine learning algorithms, since with the sum and the k-mean having similar results, the k-means is a way more parsimonious method with less computational time and power needed. So thank you very much, and have a great symposium.
Hi everyone, thanks for being here. My name is Simon Fagel-Souberan, and this is Loss of Face Identification Abilities Affect Visual and Semantic Brain Computations. So in this lightning talk, we'll be asking one question, which is what types of computations are affected in the brain of individuals that doesn't have any ability to identify faces around them. So this is a clinical condition called prosopagnosia, and here specifically we'll be studying PS, which is a pure case of acquired prosopagnosia. So PS is a lady that suffered from an edge injury in 1992, which resulted in several brain lesions in the ventral stream of the brain. So in the left occipital, in the right, occipital face area, in the left face fusiform face area, and in the right anterior temporal lobe. So we recorded a large identity EEG dataset of PS as well as 19 neurotypical, so people without any brain injury or clinical conditions, while they viewed faces, so images of different faces, animals, fruits, objects, and scenes. And in total, we recorded more than 60,000 EEG trials for this dataset. So we use RSA, or representational similarity analysis, with EEG data, which gives us for EEG basically a snapshot of how the brain computes different types of stimuli. So for example, here we see that there's a phase versus non-phase distinction. We see that there's like objects versus scene and different types of expression here. So this was done by computing RDMs, or representational dissimilarity matrices, and then we can just project this on the 2D plane here. like we can compute RDMs with EEG, we can also do this with other types of model, like models of object vision, like the visual convolutional neural net, like AlexNet, which we did for every layer from the layer activations. And we can also do the same thing with a semantic model that captures information about sentence semantics, which is the Google Universal Sentence Encoder. And then we can just cross-correlate the EEG RDMs with the CNN RDMs and the semantic RDM with the EEG RDM, which give us a time course of visual or semantic processing. Main results, we found that compared to control, PS had diminished fit with the deep neural net of object vision from layer 1 to 6. And this was found around 170 milliseconds and then again around 400 milliseconds. For semantic computations, this was also affected in PS, as shown by the diminished fit with the Google Universal Sentence Encoder. This was shown from around 100 and 170, as well as 450 milliseconds. So overall, this shows that prosopagnosia affects the similarity of brain representations with artificial neural nets of object visions, like AlexNets, which has hierarchical types of processing. And this also, prosopagnosia also affects sentence semantics, as shown in the second results. And overall, we can thus say that loss of face identification abilities affect visual as well as semantic brain computations. So thank you for attending.
Titled Comparing Machine Learning and Inferential Statistic Approaches for the Classification of Cold Thermal Pain in Adolescents with and Without Chronic Musculoskeletal Pain. Chronic pain is a leading cause of disability in adolescents, resulting in clinical deficits and reduced quality of life, yet few objective methods of diagnosing pediatric pain exist. Our goal was to assess the potential of using EEG-derived features to detect cold thermal pain in adolescents with and without chronic musculoskeletal pain using machine learning and inferential statistics approaches. A total of 160 children participated in the study, 121 of whom were in the chronic pain group and 39 healthy controls. A 19-channel wearable headset was used to collect EEG data during a seated eyes open baseline and during a cold pressor task where adolescents submerged their forearm into 12 degrees Celsius water for 2 minutes. EEG feature types of interest included peak frequency, permutation entropy, directed phase lag index, and binary graph theory outcomes, with a total of 192 EEG features included in the dataset. The EEG data was also epoched into 10-second windows, leading to roughly 1,800 data points in the pain group and 550 data points in the healthy control group. A number of supervised learning approaches were evaluated, with support vector machines ultimately determined to be the best machine learning classifier for cold pain. To compare this to more traditional inferential statistics approaches, logistic regression models were also used. And as our prior work highlighted differences in EEG outcomes between chronic pain and healthy controls at baseline, models were run separately for each group. For chronic pain patients, both the SVM and logistic regression models significantly classified cold thermal pain at approximately 75% accuracy, and this was determined to be at a level above chance. Similar results were found for healthy controls, where both the SVM and logistic regressions again were significant classifiers of cold thermal pain, with accuracies ranging between approximately 72 and 75%. In looking at the most important contribution to the model, permutation entropy was the most important EEG feature type, while theta and alpha bands were the most important frequency bands. In conclusion, EEG can feasibly and accurately detect cold thermal pain in adolescents with and without chronic pain. This work represents the first step in the development of a point-of-care system where EEG can be recorded, immediately analyzed, and automatically used to generate a report, which can help provide clinicians with objective physiological evidence of pediatric pain in the absence of self-report. Thank you.
Is it possible to distinguish between different classes of learning rules using brain-machine interfaces? Monkeys can learn to control a cursor using a brain-machine interface, and there's some really interesting studies that are able to record during the course of learning. If we zoom out, it's possible that there's some kind of cerebellar mechanism involved in this BMI learning, and maybe it falls into the category of supervised learning. One could also imagine that the basal ganglia is actually involved in this type of BMI learning, and maybe there's a reinforcement learning type rule. So our broad question is, can we possibly use neural activity in motor cortex to distinguish between different classes, and particularly these two types of classes of learning rules? Our main claim is that under certain types of supervised learning, you'll need a model of credit assignment, but that with clever experimental design, particularly if you change the decoder in various ways during learning, that this will likely be biased. Whereas if there's some kind of reinforcement learning mechanism, in particularly node perturbation, learning will be noisy and possibly unbiased. One key idea here is that we use Rnn modeling to simulate different types of learning rules. The key here is that WBMI, the readout matrix, is fixed, and it's controllable by the experimenter. Under simple backpropagation through time, you'd have to take the transpose of WBMI. However, we argue that in a biological setting, it's unlikely that the monkey would have a perfect transpose of this decoder, especially if you change it. So instead, what you'd have is a learning rule that in the backward pass uses some kind of matrix M that is partially aligned to the transpose of this matrix WBMI. And so that's the source of the bias in your learning in the recurrent weights. One can also imagine a reinforcement learning scenario where you have node perturbation that just injects noise every time step. And when you average over noise, the update will follow the true gradient defined by the true BMI decoder. So our approach in this paper is to train identical networks with different learning algorithms. And then we derive a metric to predict bias in the neural activity using the neural activity itself, which theoretically is, which is in principle accessible to the experimenter. So what we find is that learning rules are distinguishable if there is sufficient bias. And so we train many different networks with supervised learning and with reinforcement learning, changing lots of hyperparameters, including noise, nonlinearities, and so on and so forth. And we find that there's many regimes where this bias is detectable. We also play around with different architectural choices, such as strong driving feedback or non-isotropic noise. And if you are interested, please contact me. I'd love to chat more about this. We will have a preprint out very soon. And thanks for your time.
I hope you had fun getting a sneak peek at these interesting projects. You will soon find these talks, as well as the posters from the in-person counterpart of this session, on our website. Unfortunately, this already concludes the first day of the unique Student Symposium 2022. Thank you for joining in, and we hope you enjoyed this collection of talks and discussions we had today. We hope to see you again tomorrow when we hear talks from Anna Levina and Patrick Desrosiers, as well as a discussion on the future of neuro-AI in the light of climate change. See you tomorrow.